All right, so this video is kind of continuing with function transformations, and this particular video is about vertical stretches and compressions, okay? And the reason why I say it's vertical is because whenever we have particular numbers in front of x, okay, or a multiplier, if you will, a scale factor, it's going to tell us whether or not the graph is going to get taller or have a steeper slope, or if the graph's going to get more compressed or have a more gentle or gradual slope. So I use those words pretty interchangeably because sometimes they're a little bit easier to see and describe. If I say vertical stretch every time or vertical compression, it may not make sense as well as if it's a gradual slope or a steep slope. Okay. So for this particular graph, okay, the first thing we have to do is recognize what kind of function it is. Okay, so 2x squared is a quadratic. My clue was that x was squared. Okay. Then I'm going to graph the parent function just because I always like doing that. Okay. Usually it starts at 0, 0. So something like this. Again, it's not super exact, but it does the job. Okay. There's no reflection because it's not negative, so it's going to stay facing upwards or being positive or having a positive slope. Okay. And then I recognize that there's no shifts, meaning I'm not moving left or right, up or down. But I do notice that there is a 2 in front. Okay. There's a 2 in front of x. Okay. And if the number in front of x is greater than 1, that means it's going to be a vertical stretch, or the graph's going to be more narrow, or the slope of each part of the graph is going to be a little bit more steep. Where if it was between 0 and 1, the graph would actually be compressed, or it'd be a little bit more flat, or the slope would be more gradual. Okay? So for this particular function, the graph is actually going to be steeper. Okay? Or as I like to say, this is a vertical stretch. Okay? So vertical stretch, so still 0, 0, but it's going to go up a lot faster than usual. Okay? So notice how it's going up a lot faster because I'm stretching it going upwards. Okay? So that would be an example here of a vertical stretch of a quadratic. All right, next we have this function. Okay, looking at this, okay, I'm going to recognize this is a cubic function. Okay, I'm going to go ahead and graph the parent function here. So normally it starts from down here, then comes up like this, something like this. Okay. There's no reflection because it's not negative. There's no shift left and right, up or down. But I do notice there's a 1/2 in front of x cubed. Okay. And the 1/2, this is between 0 and 1. Okay. So if the absolute value of the number in front of the x is between 0 and 1, that means it is a vertical compression. Okay. So vertical compression, which is a fancy way of saying it's actually going to flatten out my graph. Okay? So it's still going to cut through here at 0, 0. But what's going to happen is, so it's going to start from down here and then take a little bit more time to cross the point 0, 0. So do you see how the slope of this green line kind of, when it makes the turn, it takes a more gentle approach towards 0, 0, and then continues the other way. So it's a little bit wider. So this graph would be a great example of being wider than usual. Okay, and this is what we call a vertical compression. Okay, number 7 here. I notice that this is a square root function. Okay, so it's a square root function. And a normal square root function starts at 0, 0. And then kind of gradually goes like this. Okay? Sort of looks like that. All right. Then I notice that there's a reflection this time. Okay? So I notice there's a reflection. And whenever the negative is on the outside, it always means a reflection over the x-axis. So my new graph is actually going to come down, but still go the same direction, something like that. Okay? So that's what my graph does. There's no shifts, and actually there's no compression or stretch with this one. It's literally just what's there in the red. So for negative radical x, that is what the graph would look like. Okay, number 10, okay, I notice that this is a cube root function, so cube root. Okay, which I know, the origin of this is at 0, 0, and kind of looks something like this, right? Sort of like a cubic function, but it's going left to right. Okay, so it's going left to right. And I notice that there is no shifts, there's no reflection, but there is going to be a vertical, with the 5 in front, that's going to be a stretch. So vertical stretch. Now notice again, it says vertical stretch. Okay, so what's going to happen is, this graph is normally going to start down here, and then it's going to come up a lot faster, and then go like this. Okay, so notice how the slope is actually got a little bit steeper than the orange graph. The orange graph is a little bit more flat and steady, whereas the red picture, again, is a stretch, meaning it's going to get taller a lot faster than usual. So that's going to be a vertical stretch. Okay, now this is a absolute value graph, so absolute value, okay, which normally starts at 0, 0, then goes here, then goes here. Something like that. Again, very, very rough sketch. I noticed that there is a reflection because of the negative. Okay, so that means my graph's going to be facing down, something like this. Okay. And then I noticed that there is the 2. Okay. The 2, that also means this is going to be a vertical stretch, which means it's going to go down a lot faster than usual, something like this. Okay. All right, and the last couple here. So we have an exponential function. Okay. Again, just getting good at recognizing all the different kinds of parent functions. So exponential, again, the critical point's at 0, 1. As we know, there's going to be an asymptote here at 0. And it will look something like that. Something like that. Very rough sketch. Okay? But then I notice there's no reflection because there's no negative. There's no shift because there's nothing with x, or on the back end with y. But there's this 3 in front. Okay? Which means this is going to be a vertical stretch. Okay? So a vertical stretch, meaning it's still going to come here, but it's going to go up a lot faster, right? It's because the slope is a little bit more steep. So this is going to be a vertical stretch, and that means it's going to be stretched a little bit higher once it crosses at 0, 1. All right, and then we have our final graph here, which is a trigonometric function, okay? So for a sine graph, okay, we know that typically the graph starts at 0, 0, and then goes up to 1, crosses down, something like that, right? Hitting all those critical points there. But you'll notice that there is a 3 in front of sine, which this is going to be a vertical stretch. But this is actually what we call, with trigonometric functions, a excuse me, this is what we call a amplitude shift. Okay, and the amplitude of a trig function means how high or how low the graph's going to go. So this time it's still going to start at 0, 0, but now it's going to go up to 3 and down to -3, where normally the graph just goes to 1 and -1. Because of the amplitude, it's actually going to go all the way up to 3 and down to -3. So it's going to look like this. Okay, so those are the different types of graphs and dealing with vertical stretches and compressions. Again, I hope this helps, and good luck with your work.